In this video, we're going to start section 6.2 on trigonometry in right triangles. So we will be reviewing some SOH CAH TOA. This is likely stuff that you would have seen at some point in high school. Our big goals for this section are to define and evaluate trigonometric functions in right triangles using SOH CAH TOA. And then we'll talk about how we can use that to find side lengths of right triangles. Okay, so before I get into the content, I want to motivate this a little bit. So imagine I had these two right triangles. And let's say one of them is kind of small and it's got a 23-degree angle. And maybe this side over here is 1, has a length of 1. And maybe there's a larger right triangle with the right angle there. And this is also a 23-degree angle. And let's say the larger angle is something like 4. So 4 times as big. Okay. So one of the things that we're going to be able to do with trig functions, with these new functions, these trig functions, is trig functions are going to give us information about particular angles. So it'll give us information about side lengths in a right triangle where this angle might be 23 degrees or other values. And having that information about that 23-degree angle will help us regardless of the size of the triangle. So even if I have a bigger triangle like I have here, that information about the 23-degree angle will still help us. Okay, so what is this information about the 23-degree angle that I'm trying to get at? Well, trig functions, what we're about to define and review, they're going to tell us information about angles and right triangles. Okay, so what are trig functions? Okay, so I'm going to draw another picture here. So I'm going to draw a side of a right triangle, and then I'll draw this base of my right triangle. So I'm going to make a right triangle. Okay, and I'm going to label the sides. So let me call this side A, I'll call this side B, I'll call this side C, and then I'm going to label one of these angles. So this angle right here, I'm going to notate it with this thing, this symbol. Kind of looks like an O with another like curly thing kind of coming down across it. So this is a variable. It's a Greek letter. It's a Greek letter theta. So when I write that thing, it's a variable. It's the Greek letter theta. Okay, and what trig functions are going to do is they're going to be functions whose input is an angle. So we're going to be plugging an angle into them. And what the output is it's going to be a ratio of side lengths. So ratio just means two things are going to be divided. We're going to be dividing two side lengths. Okay, and it's going to involve the side lengths of this right triangle. So I'm going to label some of these side lengths. So this side A is called the opposite side. It is opposite this angle theta. The side B is called the adjacent side. It is adjacent to the angle theta. Okay, and then this other side, well, this one, we know what this one's called. This is the hypotenuse. This is the hypotenuse of the right triangle. Okay, so one thing to note is, so the adjacent side is the side that's next to theta. That is not the hypotenuse, because technically there's two sides next to theta. There's this side and there's this side. Both of those are next to theta. But the one that's not the hypotenuse, that's the adjacent one. Okay, so before I start defining some of these trig functions that you likely would have seen before, like sine and cosine and so on, I want to review this kind of word tool, what's called a mnemonic device that we can use to help us remember some of them. Okay, so that's this thing SOH CAH TOA over here. So in SOH CAH TOA, S stands for sine, O stands for opposite, and then H stands for hypotenuse. H stands for hypotenuse. At this point, give the video a quick pause, maybe 30 seconds. And if you've seen this stuff before, try to see if you can fill out the remaining words for the CAH part. All right, 4, 3, 2, 1. Pause it for 30 seconds, see if you can fill out those remaining ones. All right, so hopefully you did that. Hopefully paused it to try those. Let's do them together. So C stands for cosine, and A stands for adjacent, H stands for hypotenuse, And then for tangent, sorry, T stands for tangent. Sorry, I kind of gave it away there. O stands for opposite. That one we've seen already above. And then A is adjacent. A is adjacent. So how do we use this? So we use this in kind of blocks of 3. So in blocks of 3 here. So the way I kind of interpret this is, when reading it from top to bottom, sine is opposite over hypotenuse. In fact, I'm going to start to write that down in this table. Sine is the opposite side over the hypotenuse. So in my picture, the opposite side from the theta is A, and that gets divided by the hypotenuse C. Okay, if I go to the next part of the SOHCAH TOA, CAH, that's saying cosine is adjacent over hypotenuse. Adjacent over hypotenuse. So in terms of our letters here, adjacent was B, and the hypotenuse was C. Okay, and then finally tangent. Tangent is given by the last part down here. Tangent is going to be opposite over adjacent. Opposite over adjacent. And the opposite side is A, and the adjacent side we're calling B. Okay, so typically when you first see trig functions, these are the first 3 trig functions that you'll learn about: sine, cosine, and tangent. There are 3 other trig functions that are called cosecant, secant, and cotangent, and those are just the reciprocals of the first 3. So cosecant is going to be 1 over sine theta. It is the reciprocal of sine. So if I reciprocal my sine, the A over C, actually, let me actually reciprocal in this form. Sine is opposite over hypotenuse, which means cosecant is hypotenuse over opposite. Hypotenuse over opposite. So similarly, secant is the reciprocal of cosine. It is going to be 1 over cosine. So that'll give me hypotenuse over adjacent. Hypotenuse over adjacent. And then finally, cotangent is 1 over tangent. It's the reciprocal of tangent. And if I reciprocal tangent, I'll get adjacent on top and then divided by the opposite side on the bottom. Okay, so we have these 6 definitions of trig functions involving the sides of a right triangle. So let's start doing some examples where we work with these. Okay, so first picture, I got this example and I got this right triangle, and it says to find all trig functions of theta. So that means I'll have to figure out what sine is, cosine, tangent, and then these 3 other ones, these reciprocal ones. So one thing that I'll need about the right triangle is I notice that one side is missing. This side up here is missing. Maybe I'll call it x. So let's solve for x first. If I use Pythagorean theorem, we get x squared plus 12 squared equals 13 squared. Okay, and if I evaluate and solve here, this is x squared plus 144, and then 13 squared, that is 169. So let's isolate the x. I'll subtract 144 and get x squared equals 25 if I subtract it. And then square rooting both sides, I'll get that x equals 5. Notice that there's no plus or minus here, no plus or minus, since x is a length. X is a length in my picture, so it couldn't be negative. Like ordinarily, when I square root both sides of an equation like I did here, I would need a plus or minus. But in this case, I don't, because x is a length. All right, so let me label this in the picture. X is 5. So now I know all the sides of the right triangle, so let's start writing down the trig functions. Okay, so if I first do sine, let me just get ready. I'll write sine of theta, cosine of theta, tangent of theta. So I'll just get ready. So sine theta, remember, using my SOHCAH TOA, sine is opposite over hypotenuse. Opposite over hypotenuse. So in my picture, the opposite side to theta, the opposite side is this one. It's the x. Okay, so that length is 5. divided by the hypotenuse, 13. Okay, and that's sine of theta. It's giving me a ratio of the opposite side to the hypotenuse side length, 5/13. Okay, what about cosine? With SOH CAH TOA, cosine is adjacent over hypotenuse. Adjacent over hypotenuse. So the adjacent side to theta is the one that's next to it, that's not the hypotenuse. And that's the 12. Okay, so 12 is the adjacent, divided by the hypotenuse. And nice, we got cosine. All right, tangent. Using SOH CAH TOA, tangent is opposite over adjacent. So based on theta, the opposite side is the 5, and the adjacent side is the 12. So the opposite side is the 5, the adjacent side is 12, and we got tangent. Nice. Okay, so we want the other three trig functions as well. So let's get cosecant of theta. That's the reciprocal of sine, so that is 13/5. What's the reciprocal of cosine? Well, that is secant. Secant theta. If I reciprocal the cosine, I get 13/12. And then finally, we have cotangent. Cotangent is the reciprocal of tangent, and reciprocaling it, we get 12/5. All right, cool. So we got them. So those are our 6 trig functions using this angle theta. And notice that, well, I didn't even need to know what the angle was to be able to get all the trig functions of it, because I knew all the sides of the right triangle. Okay, let's look at some more examples. So I'm going to flip that page. So let's flip that page. And the next example says, well, let's find sine of 30 degrees, cosine of 30 degrees, and tangent of 30 degrees in a 30, 60, 90 triangle. And I want to do this in two 30, 60, 90 triangles. The first where the hypotenuse equals 1, and the second where the hypotenuse equals 2. Okay, so I'm going to draw some pictures. So I'll draw a picture for A, and I'll draw a picture for B of a 30, 60, 90. Okay, so in A, I'm going to draw a 30, 60, 90. So there's my 90 degree angle, and maybe this is the 30. And if that's 30, the other side's got to be 60, because all three angles together have to add up to 180. So this first picture, I'm going to make the hypotenuse 1. That's what it wants in part A. But in part B, it says, well, now another 30, 60, 90 triangle, but bigger hypotenuse. So that's going to make a bigger triangle. So now the hypotenuse is 2, and I have a 30 degree angle, so the other angle has got to be a 60. Okay, so I have these two 30, 60, 90 triangles, but they just have different hypotenuses. Okay, so we're going to need to get what sine of 30 is, what cosine of 30 is, cosine of 30 degrees, and tangent of 30 degrees. We'll have to get all of those in both of these pictures. So even for part B, I'm going to have to do that. So let me just write that out. So I'll have to get sine of 30 degrees for this one, cosine of 30 degrees, and tangent of 30 degrees. Okay, let me just set this up. I'll write some equal signs in all of these. Some equal signs. Okay. All right, so we're going to have to remember our 30, 60, 90 stuff from the previous section, 6.1. So what were those relationships? So remember that if I know the hypotenuse, to get the side that's opposite the 30, so the side that's opposite 30 is this one, what I do is I divide the hypotenuse by 2. And that gives me 1/2. You know what, let me put the 1/2 in a different color. That gives me 1/2. That gives me 1/2. Okay, in other words, if I have this side, the 1/2, to get the hypotenuse, I gotta double it. And doubling 1/2, I'd get 1. All right, and if I have that side, to get the side opposite the 60, we multiply it by √3. And that would give me, well, √3/2. Okay, so those were just our 30, 60, 90 side length relationships. Okay, and well, in the bigger triangle, there's something I want to notice about these two triangles. I notice that all their angles match up. So these two triangles are similar. We got some similar triangles. Okay, which means the ratios of the side lengths needs to be the same. So going from the small triangle to the big triangle, we'll notice that the hypotenuse length got doubled, which means all of the side lengths need to get doubled. Okay, so let's double all of them. Okay, so first I'm going to double the 1/2. If I double the 1/2, I get 1. Ooh, whoops. I don't want to erase, I wanted to draw. So if I double the 1/2, I get 1. So that base length there is going to be, a 1. Okay, now let me do the same thing for this √3/2. I got to double that. And if I multiply that by 2, well, it would cancel the 2 on the denominator, and it would just give me √3. Nice. So if I multiply all the side lengths in the small triangle by 2, I get the side lengths we have in this big triangle. Awesome. So we got to do that because the triangles were similar. Okay, so now I have all the side lengths in both of these triangles. I'm ready to start writing down what these trig functions equal. So sine of 30, okay, so remember sine with SOHCAHTOA is opposite over hypotenuse. And what's the opposite side to 30? Well, it's the 1/2. The 1/2 is opposite, and that gets divided by the hypotenuse, which is 1. And anything divided by 1 is just the anything. So this is just 1/2. Nice. Cosine. Well, cosine is adjacent over hypotenuse. And the adjacent side to 30 is the √3/2. √3/2 is the adjacent side. That gets divided by the hypotenuse, 1. And something divided by 1 is just the something. So this is √3/2. Okay, let's do the same thing with tangent of 30. So tangent is the opposite over adjacent. And the opposite to 30 is the 1/2. The adjacent to 30 is √3/2. And now I want to simplify this. So simplifying, I got the 1/2 divided by a fraction. That means it gets multiplied by the reciprocal, 2 over √3. And multiplying these, the 2's would cancel. And this equals 1 over √3. 1 over √3. Nice, so that is tangent of 30. And if I wanted to, I could rationalize the denominator with this. But this problem didn't specifically ask me to, so it would be okay to leave it like this. Okay, now let's get the trig functions in the other 30, 60, 90 triangle, where the hypotenuse was 2. All right, so sine is opposite over hypotenuse. Opposite is 1, and the hypotenuse is 2. Ooh, so one thing to notice that these are coming out the same. So the signs were the same in both of these triangles. Let's see if that happens with these other ones. Cosine is adjacent over hypotenuse. Adjacent is √3, hypotenuse is 2. Ooh, and those are the same as well. So the cosines were the same. What about tangent? Tangent is opposite over adjacent, and the opposite is 1, and the adjacent is √3. And yet again, those are the same. So the tangents are also the same. So I want to make a note about this. It turns out that's not a coincidence. The values are ending up being the same because we have these similar triangles. And similar triangles preserve the ratios of the side lengths. So in other words, when you have two triangles like this, triangle 1 and triangle 2, that are similar, when you make the ratios of their side lengths, which is what the trig functions do, we would expect them to be the same. Okay, so that's one of the things that makes trig functions really nice. They're going to work in whatever size triangle we have, as long as you're working with the same angle in those two triangles. Like I was working with this 30-degree angle in the two triangles. Okay, so let's do another example. Now let's find all the trig functions of a 45-degree angle. So a 45-degree angle. Okay, so I'm going to make a right triangle. Right triangle. All right, so right triangle. So if one of the angles is 45, well, the other one has to be 45. So that's going to make this a 45, 45, 90. Okay, all right, so back in section 6.1, we drew the side lengths of a 45, 45, 90. In fact, we did it with two different sized right triangles. We did it with, let me draw another one as well, slightly bigger one. Okay, so we did it where the hypotenuse was 1 And we also did it in another one where the hypotenuse was, well, actually, let me not say it for the second one. Okay, because at this point, what I want to do is, I want to give you all a bit of time and see if you can remember, well, what are the other sides, this side and this side, of a 45, 45, 90? So take about 30 seconds, see if you can remember what those other sides are. 4, 3, 2, 1. Pause the video, pause it for 30 seconds, and see if you can get those other ones. All right, so hopefully you did that. Hopefully you paused the video and thought about it to get those other sides. Okay, so let's review what they are. So remember that in a 45, 45, 90, if you know the hypotenuse, to get either one of the legs, so either this one or this one, because they're both opposite the same angle, they're both opposite of 45, they're going to be the same. They got to be the same size. And what we saw back in that section 6.1 is, well, the hypotenuse, you divide it by root 2. Okay, and if I do that, I'll get 1 over root 2 here, 1 over root 2. This is also 1 over root 2. Okay, so those are going to be the side lengths in this 45, 45, 90 triangle. All right, so now, well, it wants all the trig functions. So I need sine of 45. And I need cosine of 45. I also need tangent of 45. And because it says get all the trig functions, it means not just these three, but get all the reciprocal ones as well. So get cosecant of 45, and secant of 45, and cotangent of 45. So get all 6 of them. So let's get all 6 of these. So if we work with the picture that we have, okay, so sine is opposite over hypotenuse, the opposite side to 45. And there's 2 45s here, so I could technically work with either one. But let's say I was focusing on this 45. Well, the opposite side to that is this 1 over root 2. 1 over root 2. Okay, and that's got to get divided by the hypotenuse, which is 1. And dividing by 1, well, that just leaves me with the numerator, 1 over root 2. Nice. And we would have gotten the same thing if we work with this as the 45, because the opposite of that is this 1 over root 2. And that would get divided by the hypotenuse, 1. Okay, so that's good. That's good that it's getting us the same thing no matter which 45-degree angle I work with. So cosine is adjacent over hypotenuse. So the adjacent to this 45 is, well, that 1 over root 2. 1 over root 2 divided by the hypotenuse, 1. And that's just 1 over root 2. All right, tangent is opposite, which is 1 over root 2, over adjacent, 1 over root 2. Oh, and that's just 1. So that's just 1, nice. So that is just 1. Now let's get the reciprocal ones. So cosecant, if I reciprocal 1 over root 2, is just root 2. Secant is the reciprocal of cosine. That's also going to give me root 2. And then cotangent is the reciprocal of tangent. So I'll get 1 over 1, which is 1. Nice. Okay, so we got all of these. We got all the trig functions of a 45-degree angle. Okay, when we start talking about the unit circle, often we'll see these with the denominator rationalized. So for example, with something like 1 over root 2, if I rationalize the denominator, I'd multiply this top and bottom by root 2 over root 2, because then on the denominator I get 2, and the numerator, 1 times root 2 is just root 2. So one thing to note is 1 over root 2, well, that's the same thing as root 2 over 2. And we'll usually see it written like that when we get to the next section on unit circle. Okay, so I mentioned earlier that, I could have drawn a slightly different sized 45, 45, 90. So I could draw a slightly different sized 45, 45, 90. Because the other one that we saw before was, is there something I could multiply all the side lengths by, to sort of get rid of all the fractions? Because I don't like having this fraction, this denominator here. So I would have to multiply by root 2, multiply by the denominator to make that happen. So if I multiply all the sides by root 2, the hypotenuse becomes root 2, and then each of the legs becomes 1. I just get 1. And I would encourage you to check it out, like try this as a warm-up problem. But if you used this triangle, this 45, 45, 90 triangle, to get all your 6 trig functions, you'll get the exact same things, which is what we would expect to happen. That was the same thing that happened for us in this earlier example, where we did two different size 30, 60, 90s. Okay, so these trig functions should work and give us the same values for the trig function, sine, cosine, tangent, and the other three, in any size triangle that involves that particular angle that we're looking at. Sorry, I should say in any size right triangle that we're working with, whatever angle we need. Okay, all right, so let's end with one other example. Okay, so this example is going to kind of illustrate, well, what's something that we could use these trig functions for? Okay, so it says, in the triangle below, find x and y. And we'll need a calculator for this problem, so I'm going to give you a heads up about that, to round your answer to 3 decimal places. Okay, so we got this right triangle here, and one of the angles is a 25-degree angle, one of them is a 65-degree angle, and we know one of the sides. We know this side is a 12. So one thing this picture might represent is, I don't know, maybe the hypotenuse is like a ladder. Maybe there's a ladder leaning against this wall, and x represents, well, how far is the base of the ladder from the wall? And so that might be like a real world situation corresponding to this picture, this setup. Okay, so I want to get those missing side lengths. So knowing the values of trig functions can help me identify missing side lengths in a right triangle. So let's see that in action. Okay, so let's say I work with one of the angles, like 65, and I take some trig function of it, like sine. Let's say I take sine of 65. Well, I know sine is opposite over hypotenuse, and the opposite is y, and the hypotenuse is 12. So let's isolate y. So y equals, if I multiply the 12 over, 12 times sine of 65. Okay, and this is where I'm going to use a calculator because trig functions are so common that people have just measured trig functions at different angles. So our calculator can tell us what is sine of 65, so I'm going to use it to get that. So this will be 12 times sine of 65 is about 0.906. 0.906, and actually I'm approximating here, so let me write an approximately equal to symbol. And when I do that multiplication, this is about 10.876. So 10.876. Okay, so nice. Okay, cool. So I want to show you, okay, so that's y. Let's get x. So sine was great because it helped us get y. What if I used cosine? If I use cosine of 65, well, that's adjacent over hypotenuse, and the adjacent to 65 is x. Hypotenuse is 12. So let's multiply the 12 over, and I'll get x equals 12 times cosine of 65. I'll need a calculator to do cosine of 65. So that gives me 12 times cosine of 65 is about 0.423. And multiplying these, this is 5.071. Okay, so that's what I'm getting for x. X is about this, if I round it to 3 decimal places. All right, okay, so when I did this work, I had worked with the 65-degree angle. What if I decided to work instead with the 25-degree angle? Would I still get the same values? That's going to be method 2. Let's try it. So if I did something like cosine of 25, cosine is adjacent over hypotenuse. So the adjacent side to 25 is the y, and that gets divided by the hypotenuse, which is 12. So now if I isolate the y, if I multiply the 12 over, we get y equals 12 times cosine of 25. So 12 times cosine of 25. All right. And if I use a calculator to evaluate cosine of 25, this is approximately 12 times 0.906. Okay, and doing that multiplication, I get 10.876. That's the same thing I was getting in method 1 for that example. So notice that sine of 25 ended up being the same thing as cosine of 25. They ended up both being 0.906. And we can actually see why we'd expect that from the picture. Because sine of 65 was the opposite over the hypotenuse. That was y over 12. But if I look at cosine of 25 was the adjacent y divided by the hypotenuse, 12, and that gives me the same thing. That gives me the same thing, y over 12. So we would expect sine of 65 to be the same as cosine of 25. Okay, so I won't work it out, but if I did the same thing with the 25-degree angle using sine, I'll get the same value for what x is, about 5.071. So one of the big takeaways from this is, I think like I mentioned at the start of this example, trig functions are nice when I have right triangles and I have, some of the sides, like I had this side, but I don't have the others. Trig functions can help me identify what those side lengths are. Okay, so next time, one of our goals will be, we're going to try to do trig. How should I say this? Trig for angles. What if we have angles that are greater than 90 degrees? Can we still do trig there? And it turns out yes, and that'll involve what's called the unit circle.